everybody, it's Georgia. Penetration testing, a hands-on introduction to hacking, and this time we're going to look at doing a little more advanced exploit development. This one takes a command line argument as it states. So let's see if I can pull this off without using the lab manual, because unlike the last one, I didn't write this one. Well, let's see how badly I screw this up. Alright, so there is challenge, and it does take command line input, but if we overrun it super bad, this one, I think we need like 600 or so. So this time I am going to do Python instead of Perl, and the last one I used Perl because I used Perl in the book, but I've gotten older. So I want a Python-C for command, single quote, I want to print A times 600, I think is what it takes to crash it. There's not an exercise yet, though. Like I said, in some other ones, we are going to add additional labs. I can't remember how often. I think monthly. We'll figure it out. So there will be more challenges added as we go. Certainly when book 2 comes out, a whole lot more, which means I have to record all this stuff again, which it's been fun and all, but God, it's exhausting. 53 labs. Oh yeah, sure, I can do it in a week, a month later. Anyhow, so if we want to print A times 600, and let's do close our single quotes. That time we do get a segmentation fault. So let's GDB and challenge. And this one we don't have the source code for, but we know there's going to be a main. Disassemble main. The lab manual kind of hand-wavily goes into the fact that it's taking command line input. We know it takes command line input because the challenge says so, and because we just tried it and it seemed fine with it. We do have, it doesn't matter. I can set disassembly flavor to Intel, which I just like how it looks, but apparently I can't spell disassembly. Set disassembly flavor Intel. There. Alright, so now if I disassemble main, it looks more like just Intel format is just what I'm used to. So I mean, like I said, we don't have reverse engineering yet, though I may not have said that. I may have just said it in my head. We don't have a reverse engineering section yet. There is no reverse engineering section in book 1. In book 2, there is going to be a reverse engineering chapter, so another Easter egg for those of you who are playing the labs. I'll just continue telling you stuff about the book that no one else knows. But, you're not expected to know disassembly yet. I mean, like it says, it does have the set UID. Basically, that's going to turn this into root. So it will become root, and since our flag is in the root directory, getting control of this guy would be ideal, so we could get that flag. We do have a call to a user-defined function, get input, so we can do a disassemble get input. And we can't just break on line numbers here. What we can do is break off memory addresses or locations and functions and things like that. So what I want to do is I just want to break, because we see in here we do have stir copies. So even though we don't have the source code, this is probably pretty similar to what we saw previously in our last example. It's a stir copy. We're going to be putting too much data in, so our destination is going to be too short. We're going to use our user input to put too much data there and corrupt the stack. So if we break like sometime after the stir copy, like I can do like break. This is something I always forget. You have to put the star before the name of get input, and then so I can put, say, like plus 65. So I'm right before this call to print. And that'll set a breakpoint. You don't necessarily have to set it there, just somewhere after the stir copy happens. And do remember to put I always forget this, I don't know why, that you have to put the star before the name of the function. It's just how it works. Anyhow, so yeah, let's run this. So let's run, and again, let's do our Python -c single quote print a times 600 close single quote close parenthesis. That does hit our breakpoint, so our stir copy should have happened already. So let's examine, I don't know, 100 hexadecimal words from RSP. So we're currently in get input, which is where the stir copy happens. So RSP should be the top of that stack frame. You see at the beginning of the stack frame, you've got, you know, some stuff. Not sure what it is really. But then we start to see our 41s. So we do have data that we control in the stack frame. That's not surprising because of that stir copy. You know, there's a local variable somewhere in there that is the destination for that stir copy that we saw in the disassembly. And it, just like last time, just keeps writing. This time, you know, it's not 13 A's. It's like, well, we're at 600. So our next question would be, you know, how much space do we actually have here? This is where we're going to put our shellcode. You know, last time we jumped to a function called overflowed. There is no overflowed here. This is where we're going to put our shellcode. That's like our Metasploit payloads that we've used. We're actually going to use MSF Venom like we did to make those PHP payloads and such that we uploaded to vulnerable web servers. We're going to actually make a shell. So it's going to write out all the instructions to make a shell, and it will execute them. So we're going to send control back and execute. Right now, it would just execute a bunch of 41s, which is like increment ASP or something. So not very useful. But so we're going to replace this with shellcode. So our question is, like, how much room do we have for shellcode? So there are a few ways to find this out. Like Metasploit has a pattern thing that you can use, but I actually like how they do it in the lab manual a lot. So this is kind of one of those things you have to look up. Basically, we're printing in decimal format. Okay, first I want to see where is our RBP, the bottom of the stack frame, right? So examine one hexadecimal word from RBP. So that's RBP's address right here, and so what I want to do is p/d, so that's going to print in signed integer format. So I want to know the difference between, so remember the stack grows up to lower addresses, so I want to know what is RBP, the bottom of the stack. I don't want to go to the top of the stack because I want to know like how much room I have for my shellcode. So where my shellcode will start, where my A's are. So grab where they start. So this one that E080 at the end. So that tells me that between where the 41s, those A's start in get input stack frame, and the base pointer is 512 bytes. The base pointer is also another 8 bytes, right? Because we're 64-bit, so 8 bytes for the base pointer itself. So we should have 520, and then what comes after that, it's the return address. You know, if we go back to, you know, our book, that's the lab manual. But if we go back to our book, remember we have, you know, the stack frame for this would be get input for function 1, and then EBP is at the, or RBP is at the bottom, and then right after that is the return address. So the return address, you know, that we want the control to send our control back to execute the shellcode. So we should have, so 512 plus 8 for RBP itself. So 520 bytes that we need to fill with shellcode. Alright, so let's exit out of here for now. Yes. And what we can do is use, now I actually can do a clear, MSF Venom. Remember, we saw him already to create standalone payloads, like we did it to make PHP payloads to upload, things like that. So if we do dash payload, so we want to do Linux 64, it is 64-bit, so we want to do /64, and we want shell underscore bind TCP. There are going to be ones that are like shell / bind TCP. We didn't get into that in this course. It is covered in the book that there's inline payloads where the whole payload is in one go, and staged payloads where it basically just has a stager where it has to talk to Metasploit to make this. We just want to use netcat, so make sure you use the one in the lab manual. It's just going to make a bind TCP shell. By default, it'll be on port 4444. So basically what it'll do is spawn a shell listening on port 4444. And since the challenge binary is what's going to run it, it will be running as root. So if we can get this thing to execute, we should be able to get a root shell on the box. Format -f, we're not going to do PHP or raw. It's going to be Python. Because who doesn't like Python? I know I like Python. And -b for bad characters. There is a blog post on my website, bulbsecurity.com, which is currently getting things done to it. But I'll get it fixed by the time the lab launches, so I can send people to the lab. Anyway, I'm finding bad characters, but this one I'll just give you the bad characters. It's just null. Null terminates a string, like I said in the last one, so we don't want any null bytes in our payload. So we can execute that. It will take a minute to run. What comes out of yours, because it's going to create the payload, the shell code on hex, and it is going to encode it to make sure it gets rid of any null bytes that might be in it. So then when it runs, basically it has a decoder stub at the beginning, and it will decode itself before it runs. The encoders are polymorphic, so what you're going to get spitted out is going to be different than what I get spitted out, most likely. And anyway, so yeah, we'll let it do what it's going to do. Hopefully it'll finish pretty quickly because, yeah, by this point, I think I've told you everything in the world I can possibly think of. Oh, don't make me sing. I can't sing. It's bad. Well, it's probably good that I can't sing, because if I could sing, I probably would have wanted to be a pop star and not a hacker, and then we wouldn't have this lab, and I'd probably be even more poor than I am right now. Oh, come on. Hurry up. Okay, here we go. Alright, so again, yours is probably going to be different than mine, because they are polymorphic. The main thing is that the length is 127, and we said we needed 512 bytes plus the 8 for RBP, so 520 bytes total to get to our return address. I thank the Pentester Academy team for giving me nano on this box, because I do not think I could VI my way through this. I actually already wrote the exploit, so kind of ignore it. So I copy paste in my buff from MSF Venom, so that's my shell code. I also put in up here at the top, I called it NOPS. If you're not familiar with NOPS, that's just it just means no operation. So it's 90 in hex, and it does nothing. It just literally does nothing. So we're going to use something called a NOPS sled, which is for padding. So we'll hit our NOPS and it will do nothing. The downside of NOPS is that, if it's going across in clear text or otherwise, being examined, your intrusion detection systems, that's one of the things that typically goes into their list of things that they look for a long string of NOPS, because it's probably an exploit. You may have noticed, when we were taking a look at Metasploit, one of the, with auxiliaries, exploits, post, and all that, you saw NOPS. It actually does have, NOP equivalents. It'll increment a register and then decrement it, so it's equivalent to doing nothing to avoid that problem. But for this, we don't have to worry about it. So NOP sled your way as much as you want. Alright, so, we've got our NOP. We've got our shell code, so I also put RIP as B times 8 So just, once we get to our return, our RIP was literally sitting right there. I just have B's in it for now. We don't know what we're going to have our return address be. Our return address, we're going to try to jump back into our NOPS and execute our shellcode. But for now, we'll just put it as something that will crash it, make sure our offsets are correct. So I just did B times 8. So it should come out with, it'll crash at 42, 42, 42, 42, 42, 42, 42, 42, just like we did in our last one. And then I just want to make our string. So this prints out, I kind of did NOPS times 300. So that's going to do 300 NOPS. That's why, it's a NOPS sled. You land in it and it just does NOP, 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 NOP. It does nothing until it gets to buff, which is going to be our shell code. And then I did some more NOPS. I basically just put buff in the middle of our NOPS. I don't necessarily have to do that. As long as it executes the shellcode, it doesn't really particularly matter how you do it. So since I need 520 bytes total before RIP, I put in 300, and then I did buff, and then I did NOPS times 212, which is 220 minus the length of buff. So to avoid having to do the math, I just let this, say how long is buff, and that comes out to how many more NOPS we need. Kind of a trick for people who don't like arithmetic. And then finally, I put RIP, which again is currently B times 8, because currently it'll crash, but we will replace that. You can see the commented outline here from where I ran through this to make sure it was all working before I ran it for you. So let's see what happens. All right. So let's GDB let's GDB challenge. And again, let's do our break at get input with a star plus 65 or something, and then run. And this time we want $, open parentheses, Python, and we want to run, instead of -c A's and B's and whatnot, let's do exploit.py. So that's going to run exploit.py, which prints out that attack string that we made of NOPS, buff, and RIP. So that'll become the command line input. We hit our breakpoint, and so if we look at, so this is again after the stir copy happened. So we examine, say like 100. Well, that'll hit our NOPS, won't it? How many NOPS did we put in? Like 300 or something? Oh, whatever. We'll just do 100 for now from RSP. Yeah, we see we've got our junk at the top that we don't know what it is. We've got our NOPS. So here's our NOPS sled. So again, whenever we hit the 90s, it'll do nothing. So that's why it's called like sliding down the NOPS sled, because it'll do nothing, do nothing, do nothing, do nothing, do nothing. Keep going down until it starts to hit our shellcode, and then our shellcode will execute. So as long as we can redirect execution somewhere into this NOPS sled, it will pick up execution there, slide down the NOPS sled. Again, I'm pointing at the screen as if you can see it. So it'll slide down the NOPS sled, execute our shellcode, and if we examine RBP, the base pointer, it does have NOPS in it as well, and right after that we should have our B's. So if we do like 16 here, so we get our NOPS. Remember, 8 bytes of NOPS for RBP, and then right after that should be the return address, which should be our 8 B's. B in hex is 42. So what should happen at this point, if we let it continue, is it should crash at the 42s. Sure enough, it does, but it does look like we've got our NOPS and our shellcode in place. Our offsets are correct. Everything's ending up where it's supposed to. So all we need to do at this point is replace these 42s, the B's, with an address somewhere in the NOPS sled. It doesn't particularly matter which one. I did the one that's in the lab manual just because with all those zeros and all those Fs, I was bound to type it wrong. But you can grab any address that's in your NOP sled, and that's where we want to end up. I mean, we did notice in our previous one that the location of the stack can move under different circumstances. So, if you do chapter 18 in the book, we actually jump into another location of a register. So, I do encourage you to do the book exercises that aren't in this one as well, certainly. And like I said, we will be adding more exercises. We will do Windows exploitation ones as well as reverse engineering, and add some more, we'll add some more stuff on a regular basis. And certainly, there's labs for the second book, but, this is pretty much the equivalent of what we do in the next chapter in the book. A little bit harder stuff than here's the source code and it's like 13 bytes long. This is a bit more realistic, and we're using a real payload. But anyway, all right, so let's quit. Yes, I want to quit even though there's a dead process. Go into exploit.py and comment out our RIP equals B times 8. And again, I just grabbed one. I grabbed the one from the lab manual. Remember, you do need to put it little Indian. So byte by byte, flip it around. So you got 0 zeros over here, and then, E0, you see, with all the F's and things. But again, it doesn't have to be the same one as mine. Just make sure you do put it little Indian, which does mean don't flip it around character by character. Flip it around byte by byte. So, what this would be is... let's not do that. So what this would be if I had actually grabbed it manually, it would be 0 0 0 0 7 F and F F F F F F E1 E0. So again, we're flipping it around byte by byte, not digit by digit, because it takes 2 digits in hex to make a byte. So again, it doesn't have to be that exact value, just something that'll land you in the NOP sledge. You want an address that's got 90s in it, basically. And so that should be the only thing that we had to change there. Our shellcode's in place, our NOP sleds are in place, our offsets were right. So all we needed to do was change RIP, our return address, to somewhere in the address of the NOPs, so it would execute. And we don't really need to do it in GDB now. So let's run challenge and Python exploit.py as our command line input. This time it hangs, so we don't get a segmentation fault. It also doesn't stop. So what this has likely done, assuming everything went well, is it has spawned that shell. The shell code executed, so it's should be listening for us. So if you open up a second tab, you can just hit the lab link again to open a second tab. If you do a netstat and TP, that's not the same flags that they use in the lab manual, but whatever. We have now listening on port 4444, which is again the default for Metasploit. We do have a listener. So we can just do a netcat to localhost on 4444. It doesn't actually give us a shell prompt, but if I do a who am I'm root, so we can cat out root flag. Fair enough. Right, so the main difference here, one, we didn't have the source code, but it was really the same sort of thing. It takes command line argument from the user, and it uses that stir copy function, and we overwrite all the way over our return address. So, but instead of sending it to another function, we used MSF Venom to create shellcode. In this case, since this was a set UID binary, it becomes root. So if we could take over it, we could do just what we did and grab a flag in root. And so, we did some shell code with MSF Venom, and we put it in there. We padded it with NOPs because we found that we needed 500. There were 520 bytes between, the start of our control, where we started getting 41s, to the return address. So we needed to make sure that we filled all 520 bytes. If we didn't, our return address would end in the wrong place. So we used NOPS, or no operation, which is, do nothing. We used a NOP sled to fill in the difference because in my case, the payload was 127 characters. We needed 520, so I used NOPS to fill that in. And then for the return address, I sent it somewhere in my NOP sled. It slid down the NOP sled. It executed my payload, which in this case spawned a shell as root since the binary was running as root, and that allowed me to get my flag. So, that's all for this one, and I'll see you next time, and we'll do yet another one of these. Bye.